So Adlen Ksentini is a professor at EURECOM and also a board member of the OpenAirInterface Software Alliance. In his function as a professor, he's leading the network softwareization group activities in EURECOM, in particular related to network slicing and edge computing. And in general, his research interests are network softwareization and network cloudification, software-defined networking, edge computing, and network slicing. And in general, he's interested both in systems and architectural issues, but as well as algorithmic problems. So, and in the following, he will speak on using AI for dynamic TDD configuration and OAI and ORAN approach.
Thank you, Robert, for presentation, introduction. It's my pleasure to be here. I will present our work on using AI for dynamic TDD configuration and the implementation that we have done using OAI. This work is done by my PhD, Karim Boutiba, who unfortunately was not able to join. So I will do the presentation, but I will show you a demo video about the demo. Okay, so I mean, all of you now, I hope that you heard about AI/ML that is now getting a hype. A lot of buzzword with AI since we started to think about 6G. You see this in a lot of white papers and in the call of funding of the national agency and for project. But this is not, I would say, something new. I mean, AI exists since a while, and AI for radio configuration and base station management also exists since 4G. And at that moment, it was called self-organized network, or SON. Mostly self-organized network, as you see in this picture, allow a base station to take by itself decision regarding the configuration in order to ensure what we call in management the FCAPS component, in order to self-configure, to self-heal in terms when there is a problem and so on. And at that moment in 4G, most of the SON was proprietary, and most of the base station provided by manufacturer includes some functionality. But this SON functionality are mostly dedicated to the hardware. I mean, if you take, for instance, the SON functionality from one base station, this one will not work in another base station because it's closed. Now, this is related for the SON function is related to what we call closed loop. I think one of the presentation has been talking about this closed loop for self-configuration. Generally, to implement the SON function, we need to monitor the status of the base station and the RAN, and then according to some kind of ML model or policy or intent, or even mainly using reinforcement learning, take some decision in order to correct the behavior of the base station or correct any error or any threat, or track this FCAPS component. Hopefully with ORAN, we will be able to do this SON function in a more open way, because with ORAN, I think the precedent presentation and yesterday as well, a lot of persons presented the architecture of ORAN. There are these new interface that allow to monitor the RAN component and get information on real time on what's going on. And using this interface like E2 and OAN, the system is able to understand, this to get this data and use this data and run some kind of function as an X app or R app in order to understand what is going on and implement this SON function. And also, thanks to the E2 and OAN interface, we are able to do some kind of control on the system and change the status of the base station or the RAN on real time in order to update, the behavior and correct what is wrong. So let me first give you a brief introduction about TDD. I guess most of you know what is TDD. In 5G NR, there is two-way, and in the precedent generation, we have the frequency duplex division and time duplex division. But generally, I will focus on TDD. TDD is time division where the frame organized into communication uplink slots dedicated for uplink communication, and slots which are dedicated for downlink communication. And there is switching inside the frame in order to to allow communication between the base station and user equipment. So in 4G, the TDD configuration was fixed. There are a lot of, I think 10 or 12 configuration possible between how many slots we need to dedicate for uplink in each frame and how many slots to dedicate for downlink. But this configuration was done at the beginning when you run the base station, and it's you stuck to this configuration, whatever the type of traffic. 5G introduced the flexibility where there is no predefined pattern of the frame, but you have the flexibility to define how many slots you can dedicate for uplink and how many slots you can dedicate to downlink according to the traffic. So this picture shows you the frame. So there is the slot configuration period, which is the duration of the frame. And inside this frame, you can dedicate some slots to uplink and some slots to traffic. So one of the things is that 3GPP doesn't specify how to define this numbering, how many slots you can dedicate to uplink and how many slots to dedicate to downlink. This is not standardized. It's up to the base station configuration to derive this number. So our objective here is to use, the machine learning and AI in order to create and configure the TDD configuration on the fly. So just to recall, TDD is really something I would say interesting for private deployment because the spectrum is limited. So TDD is mostly very efficient for spectrum limited when you have a small spectrum. So in most of the TDD deployment of the big operator, most of the traffic is downlink because the user are more interested on streaming, on surfing on the internet, and so on. But if you go to the private communication or even the new service that appear with 5G, and I hope that we'll see also this in 6G with the metaverse and so on, there will be more equilibrated traffic, which means there will be more uplink demanding application than downlink, which means that the I would say the rules that we've been having before that most of the traffic is downlink is no more valid. So this will need this type of SON function in order to derive how many slots I need for the uplink and how many slots I need for the downlink. So this will allow the base station to adapt itself to the traffic. So the base station automatically will derive how many slots it will dedicate to the uplink and how many slots dedicate to downlink just by monitoring how the traffic is going in the cell and then derive this optimization. To do so, the approach that we envisioned here for this work is to use deep reinforcement learning. So this deep reinforcement learning will have, like in classical reinforcement learning, there is an agent. This agent will sit at the base station. It will look to the traffic status, which means how many traffic is seen in uplink and how many traffic is seen in downlink. And then according to this observation of the system, which is like monitoring what's going on, it derives how many slots is needed or how many slots are needed for the uplink and how many slots are needed for the downlink. So in our case, this information regarding the uplink traffic and downlink traffic are available easily at the base station. There is just a need to look to the queue in downlink, which are available at the RLC level. And at the uplink, you know that there is this buffer status request and report, which are sent by the user equipment that indicate how much traffic the user equipment have on their queue. So this one slide here is just to give you, the theoretical approach. So generally speaking here, the state that the agent look to and is used to configure the system is composed by the size of the different buffer in terms of uplink and downlink, which is state T. And the reward function is the one that derives the policy and help the reinforcement learning agent to decide how many slots to give to the uplink and how many slots to give the downlink. This reward function is very simple here. Its aim is to avoid buffer overflow, because buffer overflow at the different queue means that we lose packet, and this will impact the service performance. Actually, we implemented this DRL or reinforcement learning agent as an XApp. First, this agent has been trained using our simulator. We have a EURECOM MATLAB simulator regarding L2 and L1. I think Robert used it, and also I think Florian did it. So we trained this model there, and then we just integrated to OpenAirInterface, and we run it using rail traffic. So the implementation is shown here. So for the XApp, we use the ONF micro-ONOS rig. And the same setup has been done also with FlexRig. We use micro-ONOS because most of our clustering platform is based on Kubernetes. So we implemented the flexible TDD on OpenAirInterface, which means that at the OpenAirInterface level, the base station get request from through the E2 how many slots to dedicate in uplink and downlink, and this has been implemented in OpenAirInterface, where the flexibility of the TDD change is done after each period. Okay, so you have seen in this demo, so the advantage of using this automatic configuration. So imagine that in private network, where the one that deployed base station has no knowledge about this low-level configuration. We give the model, we throw it, and then automatically base station is configuring itself in order to adapt to the traffic and realize the optimal balance between uplink and downlink. So I mean, now as takeaway and the conclusion, programmable run, this is something that I would say happened more than 6 or 7 years ago. I think Robert started working with Flex Run, which was one of the first programmable run. Now with ORAN, I mean, we have the advantage of this open interface between the run and the controller, which is RIG. So we can develop a lot of kind of application, and one advantage is that this application that I have shown here can run on top of any base station that implement the E2 interface. And this, I would say, in my opinion, one of the advantage of ORAN by report to what we have seen before in the closed 4G. So this portability of the application among the different, base station, whatever I would say the manufacturer. So I mean, only imagination can limit the innovation with this new architecture, which is ORAN. Thank you for your attention, and I would be happy to answer your question.
Okay, very nice. Well, thank you for that. First question is, when you were applying the ILM for decision making like that, clearly shows that you can build the ILM model, right, for making a decision like applying the different application like what you did. One of the challenges for that is that if the environment or the scenarios have changed. So I think in your case, you were looking on the training environment and some very specific scenarios, and you were training right under that scenario, if I'm not mistaken. So what do you anticipate that from the training model will work as well if the TDD configuration changes, and do you anticipate keep training for every case, you have to train a new model, or how do you think that applicable will your training model in this situation? Thank you.
Okay, thanks for the question. I mean, the model has been created in a sense to avoid this kind of problem when you change the configuration of the size of the frame and so on. Because if you see here, I need a pointer.
What is this here?
Okay. So if you look to this simple, the state of the network is not the configuration of the TDD, but just the status of the buffer, which means that we are completely independent from the configuration. And the action that we are applying is not exactly the number of slot, because I didn't mention it here, but the percentage of slot that should be dedicated for uplink and the percentage dedicated downlink. So by doing this, we avoid all the relation with the configuration, and we are completely, I would say, independent from this. And whatever the configuration, the system will work. You're welcome.